Welcome. So today we're going to look at trigonometry, and the players for that are what are known as sine, cos, and tan. If you're following along, this is lesson 3. And what's going to happen is we're going to skip this part because we actually didn't do this original worksheet as of yet. And we're going to move along just into part 2 here. First off though, I'd like you to recall the Pythagorean theorem because we are going to need it. So the Pythagorean theorem is as follows. Okay. It has to do with triangles, and they're very specific. These are for 90-degree triangles, and it would look something like this. We say the long side's the hypotenuse. I'll call it C. And the other two sides, A and B. And they're related by the Pythagorean theorem relationship, which is as follows. So if we want to put some numbers on this, why don't I say I know that this is 6, this is 3. Why don't you pause the video and see if you can figure this out, and I'll be right back to show you. Okay, did you find C? Let me show you the steps. Okay, well, C squared is equal to A squared, so I have to square 6 and add that with B being squared, which is 3. Okay, so that's 6 squared plus 3 squared, or 36 plus 9. So C squared is equal to 45. You'll square root both sides and end up with C equals root 45. Or you could say it's approximately equal to 6.7. So that's Pythagorean theorem, which is something we're going to use throughout trigonometry. Let's now move into trigonometry. And to do that, we have to talk about trigonometric ratios. Okay, have a look at the Pythagorean theorem. It relates 3 sides. But the thing is, triangles have 3 sides and 3 angles. So trigonometry is an area where you're able to relate the sides of a triangle with the angles. So let's show you how it's done. If we take this triangle, first off, it's really important to notice, and we're going to do this for the next number of lessons, this triangle is 90 degrees, as is this one. The first few trigonometry skills we're going to learn are going to focus only on 90-degree triangles. Okay, and if we have a 90-degree triangle, we know that this long side is the hypotenuse. So I'll just write H. Okay, and this long side, also the hypotenuse. Now, like I said, if we're going to start relating sides with angles, we're going to need an angle. So the angle I'm going to go with, very common one, you sort of draw an O with a line through it, a little bit like an egg. It's called theta. It's a Greek letter, and it's quite often the variable used to measure angles, and in the units of degrees. So 10 degrees, 30 degrees. Okay. Now we're going to start looking at relating theta to the sides. Well, if this is theta, and we have this long part, which we call the hypotenuse, we're going to need names for the other 2 sides. And this is what we've come up with. Since this side opposes theta, sort of like his opponent, they call it the opposite. So I'll put an O for opposite. Then down here, beside theta, they call this side the adjacent side. So I'll put an A. So we can now see that this angle can potentially have a relationship with the hypotenuse, the adjacent side, and the opposite side. And we use these three, I guess, they're not really, they're just names for this. And what they do is they relate what's called ratios. So there's the sine ratio, the cosine ratio, and the tangent ratio. And instead of writing out SINE or COSINE, we use abbreviations. So we say sine, cosine, tangent, but we just write SIN, COS, and tan. And what you're going to do is you're going to take the sine of theta, and it's going to equal, it's kind of like a formula. So let's dive right in and show you. So the sine of theta, like I said, it's a ratio. So if I take the sine of theta, it's the ratio of the opposite side over the hypotenuse. So we write opposite over the hypotenuse. Next one, we take the cosine of theta, and it's a ratio again, but this time it's the adjacent side. So A for adjacent, and the H here and here are for the hypotenuse. Tangent now is the opposite over the adjacent. And you're thinking, wow, that seems like a lot. But don't worry, we've got a memory aid to help us remember this. Okay, this is the last time you'll actually write this all out, because you're going to do the following. You're going to say the sine of theta. Yes, it's the opposite over the hypotenuse, but why not write it like this? Capital O over capital H. And for cosine of theta, you write capital A over capital H. And for tan of theta, you write capital O over capital A. And if you want to start looking at this as another way, let's just change that to S with purple, C there in purple, and T in purple. And there's this memory aid, as I mentioned, and it's the following. So sine S is O over H. That's like so. S-O-H. Same thing goes for cos, C-A-H. So ca. And T for tan, T-O-A, TOA. And the memory aid we use is right there. S, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And an even better way to write this would be sine. It helps me remember it if I say the sine of theta, I'll always take the opposite and divide it by the hypotenuse. So I write it like that. The cosine is the adjacent over the hypotenuse, and the tan is the opposite over the adjacent. SOHCAHTOA. That's what we say. We say SOHCAHTOA. And it just helps us remember these three critical trigonometric ratios. Let's go back. A while ago we talked about this triangle. We said let's put theta here, and then across from him, or his opposition is the opposite. The hypotenuse is always the long side, and the adjacent's the other one. That's what that looked like for that triangle. We go over to this triangle, and this time we put theta here. So we want to know how to reference and relate this angle to the three sides. Like I said before, you start at theta and you find which side's opposite. It's almost like this is a goalie, and who's the opposite goalie facing him? Well, the only way to get across from that theta to another goalie, if you want to think of this as two goalies, they're opposing each other, would be over here. So that theta's opposite is this side here. Okay? The hypotenuse never changes. In fact, it's always across from the 90-degree angle. And the leftover side is the adjacent. So you could also use SOHCAHTOA and relate the sine of this angle. So the sine of that angle is his opposite over the hypotenuse. Let's put some numbers on this in the next few examples. So some examples. First one here, let's find the trig ratios, so sine, cosine, and tan, for angles theta. There's theta. And the other angle, we're going to name it beta. It's just another Greek letter that we often use to represent angles. And as needed, we'll go to 4 decimal places. So first thing I notice is I do have a 3 on that side, a 4 here. I'm missing this side. Can you guess it? Pythagorean theorem. So work out the Pythagorean theorem on that and catch up with me and see if you can get it right. Pause the video, come back. Alright, so there's the calculation. And it works out that that side here, I called it capital H for hypotenuse, and it's 5. So I'll put that as 5. So now we want to find the trig ratios, and we said the memory aid we wanted to use was SOHCAHTOA. So let's write that down. You'll want to write that down on all the questions you do for a while yet, until you can get it memorized. So sine, cosine, tan, SOHCAHTOA. Okay, so if we want to find the trig ratios, there's always 3, sine, cosine, tan. And let's go in order. Okay, let's do it for theta first. So here's theta. So who's his opposite? Remember we said it's like hockey? Who would these two be? Like think of them as two goalies, and they oppose each other. So that angle's opposite is 4. The hypotenuse is always the longer side, across from 90 degrees, and this 3 is the leftover. He's adjacent. He's actually, adjacent means like beside the angle theta. So he's beside him, adjacent to him. So now you can see SOHCAHTOA is written out like this. So the sine of theta, the sine, I have to take the opposite and divide it by the hypotenuse. So I'll just write it out, op over hypotenuse. Okay, so what is my op? Oops, I wrote an H here, should have been an O. He's opposite. So sine theta is my op 4 over H, which is 5. So 4 over 5. Okay, which we know to be 0.8. Keep going. Cosine theta is adjacent over hypotenuse. Cosine is adjacent divided by hypotenuse. And have a look at your diagram. 3 over 5. That goes in your calculator, and you realize that that is 0.6. Now the tan of theta is the op over the adjacent. Tan is op divided by adjacent. And you look at your diagram, his opposite's 4, and his adjacent's 3. So it's 4 over 3. We get a bunch of decimals when that goes in our calculator. So let's go to 4 decimal places with 1.3333. Okay, and there you have it. We have the 3 trig ratios for angle theta. Now let's find the 3 trig ratios for angle beta. So I'm actually going to redraw the triangle. So pause the video, try that, and catch up with me. Okay, I've redrawn this triangle over here. And the reason I do that, now I'm referencing off beta. So beta's opposite is 3. The hypotenuse is always the same. And adjacent to beta is side with 4. So now I can write his 3 trig ratios, again with SOHCAHTOA. So sine, this time beta. Now, I know it's op over hypotenuse. So I'm just going to look at my diagram. Op is 3. Hypotenuse is 5. So I'm going to write that out. Op 3 over 5. And we know that to be 0.6. Now cos beta. And we look at our SOHCAHTOA. We want the adjacent over the hypotenuse. So my adjacent's 4 over the hypotenuse, 5. 4 over 5, that's 0.8. tan of beta. Okay, well, again, the opposite over the adjacent when it comes to the tan, or the tangent's the full name. And let's look at our diagram. 3 over 4, which is 0.75. In example B, I would like you to try it, but first I'm going to set you up. Let's find side x here. He's unknown, but thanks to Pythagorean theorem, we can relate the three sides. So I'm just going to write that out, pause, and be right back. Okay, I'm back. So the long hypotenuse side is known, it's 8, and I have to square it. And the other two short sides, and this is a 90-degree triangle, one's x, the other's 5. I have to square them, add them up, and that's the relationship for Pythagorean theorem. So now I need to solve this. So this is 64. X squared still x squared, plus 25. You have to send it over. Okay, and you'll get 64 take away 25. Equals x squared, and that's 39, which means x is root 39. I'm going to leave it as an exact number for now. Okay, so now you know that this is root 39, and if you're dealing with excuse me, theta, well, he's opposite, he's adjacent, he's the hypotenuse. So now I'll draw out the other triangle so we can reference for beta. Again, you're just drawing representative diagrams. They're not to scale necessarily. Try and make them so they're roughly to scale so they feel okay, but that was theta, beta. This is 8 root 39, 5. This time, if we're referencing off beta, maybe think back to that hockey analogy. Who is opposite beta? Beta's opposite is this side. They're like facing each other. Okay, so he is now opposite when it comes to beta. Hypotenuse never changes. And adjacent is right beside beta. Okay, so pause here. Try writing the 3 trig ratios for theta and the 3 trig ratios for beta, and come back and check your answers. I'll work it out. Okay, here are the answers. So I worked out theta's trigonometric ratios and beta's trigonometric ratios. One thing to note, when you get to say this one, sine beta is root 39 over 8. Here's how it's going into my calculator. Okay, so there's my square root button. I need to hit root 39. I can hit equal if I want. I get that answer, and then I divide it by 8. And I get 0.7806, 0.7806. Or you can do it in one shot and go root 39 divided by 8, 0.7806. So as we look at what we've done, we've sort of said now we can relate sine theta and it equals 0.625. What does that really mean? Well, that's what we're going to look at next. What we're going to do next is essentially going to change us. What it's going to change for us is instead of saying sine theta equals 0.625, we're going to get to find out what theta is. And remember, theta is an angle. So we're going to go find out how we move from here to actually get the value of the angle. Now you want to grab your scientific calculator. This is the one you're going to use when you're writing your quizzes, quests, or tests, because you have to have this calculator in the right mode. We're going to be measuring angles, and as you're very familiar with, we usually use degrees, and we will always use degrees, but there are other ways to measure angles. So grab your calculator. I'll show you mine. Here it is, obviously, and you can't really tell. I know there's a bit of glare in that, but right here on mine, there's a D there. See if I can get it to zoom. Take my word if you don't see it, but there's a D there. And that means it's in degrees. So check your calculator. And I'll show you how you change mine. So if I hit this mode button, and I keep going through the menus, okay, I'm just going to keep going. Eventually I get to, there it is. Angles can be measured in degrees, which is what we want, radians, RAD, or gradients. If your calculator is in radians or gradients, you'll never get the right answers. So you just have to figure this out once and make sure your calculator is always in degree mode. So for me, I had to go to mode, and then I go pick degrees. So you can see it says 1 degrees, and I'm going to pick that, number 1. I was already in degrees, and it always has a little indicator. For me, it's this D. So you want to be in degrees. All the angles we deal with are in degrees. Make sure you have that, or you just can't do this trigonometry. So it turns out that every angle that exists, 60 degrees, 110 degrees, 380 degrees, 1060 degrees, they all have their own value for, say, cosine of that angle or tangent of that angle. So if you take cosine of 60 degrees, we know it's the adjacent over the hypotenuse, because it's ka, adjacent over hypotenuse. But you're always going to get the same answer for cosine of 60 degrees. So let's take a look at these two examples in A and B. And it sort of helps show that if you know the angle, well, you'll know the ratio too. Part B, if you happen to know the ratio, which is like all the examples we just did, we worked out the ratios. Right? We got sine B, there's the ratio, 305 is 0.6. We can actually know the angle. So we're going to kind of show you how we get there now. So grab your calculator. And the first one it wants you to do is the cosine of 60 degrees. Well, your first thing you're going to want to do on your calculator, did you put in degrees yet? Because that's important. Make sure you've done that. After that, you've got to find these buttons, sine, cosine, and tan. And all you need to do, if I want to find cosine 60 degrees, for my calculator, I have to hit cos, let me clear it, cos, put 60 in, and it knows its degrees, and hit equal. And the answer is 0.5. So let's write that down. Okay. Now the sine of 27 degrees, all I need to do, I'm going to clear it, sine button, and then 27 degrees. Let's take a few decimals there, 0.45399. And then I can do tan. There's my tan button of 68. 2.4751, I'll round it. You always want 3 or 4 decimals if it's a long decimal number. You want to maintain some precision. Okay, so cos 60 all the time gives 0.5. Sine 27 will always give that number, and so forth. Let's go the other way now, and this reminds me of the example we did in number 1. We had like cos theta and it was equal to some number, and this is how you get theta. With it saying cos theta equals 0.3256, you kind of have to undo cos theta. So to get theta by itself, you do the inverse cos. You write it like this, cos exponent minus 1 of that number there. So it's the inverse cos. Inverse is what that means. Like undoes the cosine, so it's the inverse of it. To do that in your calculator, instead of hitting cos, you'll have to hit shift cos. Or maybe your calculator has second then cos. Watch how mine works, okay? So I'm going to go shift cos. You see how it brings it up, exponent minus 1? And then you put the number in, 0.3256. And it will take that, hit equal, 70.99 or 71 degrees. So the angle is 71 degrees. Okay, let's try that with the next angle. So if I want beta, I have to do the inverse sine, 0.8290. That's how you write it. This means beta equals the inverse sine of 0.8290. Let's try that on here. Okay, so again, I have to take the inverse of my sine. There's sine, so I'm going to go shift sine, and then I put the number in, which is 0.8290. Okay, ready? 55.996. Round your angles to whole numbers. We never want decimals on our angles. So that's 56 degrees as a whole number. And make sure you have units, 56 degrees. Pause the video now, try tan, and find me the angle. That symbol there is alpha, another variable to represent angles. So find me alpha. Come back when you're done. Right, here it is. So you have to take the inverse tan of 9.5144, round that, and you get 84 degrees. Okay, so that's how we move from ratios to get the angle. And something interesting to do, now that we know alpha is 84 degrees, watch, you can go backwards. What if I hit tan 84 degrees? What do I get? Of course I have to get the same thing. You can just keep going forwards and backwards with this. Shift tan of that answer, and I'm just going to go back to 84. If I tan that, so they undo each other, and you keep reverting back and forth. Okay, so we're going to move on to example 3. We'll do one here, maybe two, and the rest we'll do in class together. Let's look at question 3, where we're given a 90-degree triangle, and we're asked to find angle theta and angle beta. Now, you'll almost never need to find sine cos tan for theta and sine cos tan for beta. You don't have to do, that would be 6 separate calculations. Usually you only have to do a couple, and there's always a couple ways you can even do them. At the end of the day, you're always going to get the same answer regardless which way you choose. In question 3a, I see I've got a right angle triangle, side 6, side 4, and they did not give me the hypotenuse. But it doesn't ask me to find the hypotenuse, so it's going to turn out that I don't need it here. It's good to start usually with any angle. Make your life easy. This sort of sounds like a good spot. It's right here. Let's look at theta. Okay, so let's focus on referencing off theta for now. If I do that, remember, across from theta, two goalies facing each other. He's opposite. That's the hypotenuse, and this would be the adjacent. Next, you're going to write SOHCAHTOA out. Let's write it out this way. And here's what you do. Theta has his adjacent known and has his opposite known. We don't know the hypotenuse. Now I realize you could Pythagorean theorem this and go get it, but save yourself that because you can get it directly with SOHCAHTOA. So since we know off theta we have the A for adjacent, I write out SOHCAHTOA and then I underline A if I see it. Okay? He's known. Over here, the opposite's known as well. So I'm going to look through SOHCAHTOA for O, opposite, and underline it. Why you do that is because this sort of reveals to you which of the 3 trig ratios you'll pick. And being tan is op over adjacent, you have op and adjacent, you want to go with the tan ratio. You only want to pick one of the 3 ratios. So in this case, since we have tan chosen, let's write it out. The tan of theta is op over adjacent. Let's go this way this time. Tan of theta. And let's put our numbers in. Op's 4. I say op to mean opposite. And adjacent is 6. So tan of theta is 4 over 6. Let's keep going. Tan theta, well, that would be what? 0.666, and it would just repeat. And like I said in the previous example, once you know the ratio, you can convert this to get the angle. Theta is tan inverse of 0.6666. You grab your calculator, and you have to put the value in and do the inverse tan. So I'm going to go shift tan 0.6666. I'll just put a bunch of 6's. And I end up getting, what is that? 34 degrees? 34 degrees. So theta is equal to 34 degrees. That gives us one part for this question. We know theta. You'll always know the second angle in the triangle. It's always 90. How will we get beta? Do you think we want to run through another trigonometric calculation? We could be a bit smarter about this, and we know that all triangles, every triangle that exists, their angles add up to 180. So if we want to find beta, let's use that rule. Beta, well, all the triangles add up to 180. So if we take away the 90-degree angle that we know, that one there, and we also take away the theta we just figured out, you will find beta. And it's much quicker than going through another trig calculation. You want to find shortcuts like this, or you want to use proper angle theories to save yourself some calculations. And in this case, beta would have to be 56 degrees. Let's try 3C. 3C, okay, we got to find theta and beta. This time I'm going to start with beta, and I'm going to work out my references. So this side here, again, it's sort of like who is opposing beta, who's his opposite, which two goalies are facing each other. One goalie's here and the other goalie's over there. That's the opposite. Okay? 8 would be the hypotenuse. It is the longest side. It is across from 90 degrees, which leaves this to be adjacent. I write SOHCAHTOA out. And I go see which ones I have. So off beta, I know my adjacent. So let's go through SOHCAHTOA and look for A adjacent. And oh, I don't know my opposite, so skip him. But I do know hypotenuse is 8. So H, H. Okay, this time I need the cosine. So I'm going to write cos for cosine of this, not theta. I wanted to say theta, but it's cosine of beta, right? Because I'm referencing off beta. And the cosine is adjacent divided by hypotenuse. So it's A over H. And let's continue by replacing. A is 7. H is 8. Okay. And now we're going to go after beta. So 7 over 8, 0.875. Okay. And you have to use the right form. So beta is inverse cos 0.875. And that goes in your calculator. Shift cos will give you inverse cos, and you get 29 degrees. Great, so for this triangle, we know, well, the 90-degree angle. We know beta is 29 degrees. We also know the triangle should add to 180 degrees. So to get theta, you use that rule. The total of 180 degrees for a triangle. Subtract away the known value of 90, which is this corner angle. Take away the 29-degree angle we found for beta, and it goes in your calculator, and you end up with theta is 61 degrees. So bring your questions to class. We have some practice work to do. We'll take up some more examples. See you soon.